Hello, in this video I'm going to do a derivation of the velocity and position functions for objects in free fall with air resistance. I'm going to cover topics in differential equations, particularly separation of variables, topics from Calculus 2, specifically partial fraction integration and some other integration techniques, and lots of precalculus, which one of the highlights there will be studying the inverse hyperbolic trig. So I'll go through the derivation, hopefully in a real thorough step-by-step process, so you can really make some connections to these earlier topics of Calc 2 and Pre-Calc. And this is meant for a differential equations course. Okay, I will start with the idea that force is mass times acceleration. And when I study the free fall of an object, I will look at the weight of the object, which I'm going to write with a negative mg. M is the mass of the object, g is a constant acceleration near the surface of the Earth, and I'm going to put a negative to indicate that it's a downward force in the coordinate system I'm creating. Now, opposite to that weight is this air resistance, which I will express as some constant k, so drag coefficient or coefficient of friction, and it's scaled with the velocity of the object squared. So this is a model for the combination of forces, the weight, which is the negative mg, and the air resistance, which will be greater with the greater velocity, and it'll be directly proportional to the square of the velocity. And so that's the force, and that's the sum of all the forces that I'm going to model here. No wind, for example, no other acceleration besides the gravity and the force of the air resistance. Those are the only forces. And that combines to the total mass times acceleration. And I'll write the acceleration as the derivative of the velocity. We could say this is a first order, and it's a nonlinear differential equation. And it's nonlinear because of this v squared. So it's a derivative of v with respect to t, and it has v squared in the equation. So it's a nonlinear first order differential equation. So let's rewrite it this way. And then a very common thing to do in studying differential equations is to isolate the derivative. So let's say dv dt, particularly if it's a first order. So I'll divide everything by m, negative g plus k over m v squared. So this is a expression right here for the acceleration over time, and you could see that, for example, if I started with zero velocity initially, the acceleration is exactly the acceleration due to gravity, but then as the velocity increases we have a reduced acceleration, because this is basically adding into this negative and making it a smaller value and a smaller absolute value. So the acceleration is decreasing as it continues to fall and pick up velocity. So one of the first things we could do is to figure out, this is what's called an autonomous equation, and that's because there's no the g, k, and m are all constant, and the only variable on the right hand side here is v. There is no factors or terms involving t, which is the independent variable, and since it's only v and a bunch of constants, that's called an autonomous dE. And they're really nice. When you have the autonomous dE, you can find critical points in terms of the dependent variable, and that critical point here is a very meaningful physical value. It's the terminal velocity. So what we would do normally with an autonomous dE is set it equal to 0, set this right hand side equal to 0. So we solve negative g plus k over m v squared equal to 0. So we've got k over m v squared equal to g. And let's start a new page here. We've got k over m v squared equal to g. So v squared equals g times m over k. And I'll take a square root in general, algebraically, I have a plus or a minus. I'm going to write mg because that I know represents the weight, and then over k. Now, in the model in which I'm describing an object that is just falling initially from rest, I'm going to take an initial velocity of 0 and just let it drop. And so in the coordinate system that I created as I first wrote that first line of the DE, down is a negative. And so actually the terminal velocity is negative square root mg over k in the coordinate system where down is negative. The terminal velocity is the velocity when the acceleration has reached 0. So initial acceleration was gravity, but then it's going to drop in absolute value it'll be less and less negative until it reaches zero acceleration, and the velocity will be actually more and more negative until it reaches a certain maximum negative value, which is that terminal velocity, which is the fastest it's going to fall, considering the drag coefficient and the mass. It'll reach a point where the air doesn't allow it to accelerate anymore, and it's reached its terminal velocity. So what we're going to do now is we're going to go back and look at that differential equation, dv dt equal negative g plus k over mv squared. We're going to look at this. You can see that when that's 0, that's when the acceleration is 0, and now what we want to do is solve this dE for v. So we can, and then I can integrate that and find the height, and that's the major purpose of this video is to figure out a formula for the velocity from just that starting point where I simply laid out the force is mass times the acceleration, and the force was the sum of the weight and the air resistance, and those were the only assumptions I made. And I'm going to assume that at time 0 it's 0, and I'll put in like a height at time 0 is like some fixed height, and from that I can derive velocity and height functions in terms of these constants. G is acceleration due to gravity, and k is a coefficient of friction, and m is the mass of the object. So from just that I can derive the position and the velocity. It's pretty amazing. Okay, let's get to that. Okay, so now we'll really get into it. We've got dv dt is negative g plus k over m v squared, a first order nonlinear dE, which is autonomous, and we found the critical point. So we actually know limiting value for v. We know that there's a terminal velocity to which it's going to approach, and we'll start with v of 0 equals 0, and we'll solve for v. Now to do that, it'll work with separation of variables because I can take k and m and g all to be constants. In fact, let's take g positive and k positive and m all positive. That'll be helpful later to take all of these values positive. So my negative is part of the equation. The negative indicates a downward force, and therefore positive is up. And so with all these initial conditions, this differential equation, we can solve for v by separation of variables. So we'll write that as 1 over negative g plus k over mv squared. If I bring all these terms as a factor over to this side, and then I'll just multiply both sides by dt, then I have separated the variables in the sense that everything involving v is over with the dv, and everything involving t is over here, but there were actually no factors or terms involving t, and so everything involves v, and it's a bunch of constants, so that separates nicely. So that means I can integrate both sides. If I integrate both sides, I'm going to need to figure out an antiderivative for this thing, and I'm going to write it a little bit differently. Let's write it like we're working on 1 over, let's say, k over m v squared minus g and integrating with respect to v. And that'll be one of the big accomplishments to figure this thing out, and we can do this with partial fractions and we'll get an ln, and then we can take that ln and write it as a hyperbolic trig, and that'll be some pre-calc that'll be useful to write it in that other way because then it'll be easier to go further. Okay, so let's work on this. Let's say in order to get this one, I'm going to just change it into, basically I've got a constant that I can come back later and write k over m, but I've got a lot of fractions here. It'll be easier for me to just call that a is k over m, and I know that a is positive because I know k and m are both positive, and so I'll say a, and for the moment I'll just call this x. And I'll just say this, so and the minus I'm not going to I'm just going to keep the minus in the formula, and so b is really just the constant g, but I want to look at this as a Calc 2 problem, which is partial fractions. So let's work on this for just a little bit, and then we can come back and plug in a was really k over m, and the b, that was really g, and let's do it that way. Alright, and I know that b, g, they're all both bigger than 0. Okay, so I'm going to come back to this and I'm going to work on that. Now if I'm in Calc 2 and I'm doing partial fractions, what I would do is take this ax squared minus b, this is a rational expression, and I'd factor it. Okay, so that means we need to factor this ax squared minus b, and the way I'll factor it is the square root of ax minus b and the square root of ax plus b. And in partial fraction decomposition you come up with these two fractions. Oh, I'm sorry, that's got to be a square root b. Another way to look at that is that I could just find the zeros, ax squared minus b, set that equal to 0. So we have ax squared equal b. So x is plus or minus the square root of b over a. And yeah, you could use those as, you could do x minus one of them and x plus the other. That would actually work, but that's not really the way I wrote it. So let me see if I can think of one other way to say that. I guess what I would have to say is that what I just did there was to break this up as a difference of squares, even though a didn't look like a square. A is the square of the square root of a, and all of this is legit because of this. Let's take, I can say a is greater than 0 and b is greater than 0, and so I'm not concerned about complex numbers here. Okay. So in order to figure out the a and the b, I have a quick way of doing that. I call this cover-up method. And the cover-up method, what I would do is I would look at this denominator, figure out when it's 0. So let me get these other things out of my way here. When is, for example, this denominator here, when is this one 0? And it's 0 when x is the square root of b over a. So if I plug that in this fraction here, I should do this something different here. Actually I need to just move all that over. Learning this new program. I should say, let's first factor it. The factors would be, now I'm going to break it up into two fractions, and in partial fractions we have to figure out what those two partial fractions are, which means finding the a and the b. Okay, so to find the a, what I do is I figure out what makes that entire denominator 0, and that would be when x is negative square root b over square root a, or the square root of b over a. And anyway, in order to figure that out, you could, once you have that, you plug that in this left-hand side here for x, and then cover up that factor that goes to 0, which means, like, for a moment here, you have to pretend that's covered up. I can't really cover it up with my hand, can I? And I don't really see any option there. So, yeah, so I cover that one up, and I plug in this in here for x, and I'm going to see that the square root of a cancels, and I get a minus root b and a minus root b, and so I'm actually getting a is, trying to do this in my head, negative 1 over 2 root b. And we can do b the same way. If I just figure out what makes that denominator 0, that would actually be when x is square root b over square root a, and by this quick cover-up method I'm looking at this entire left-hand side right over here, and I'm plugging in that factor that made this fraction here 0 on the bottom, and when I plug it in I'm going to get that guy 0, but I cover that up and I see that when I'm plugging it into this whole entire thing with this thing covered up, the root a cancels and I get root b plus root b, so that's 1 over 2 root b. I'm sounding like root beer, but it's root b. Okay, that's now the partial fractions are done. So I have 1 over ax squared minus b is negative 1 over 2 root b divided by root ax plus root b, and then plus, and now I figured out what b is. B is this thing. It's 1 over 2 root b, everything divided by root a x minus root b, like that. And that's what I need to integrate. So we go back up here and say integral of, alright, negative 1 over 2 square root of b, everything divided by square root of a x plus square root b plus, and then this term 1 over 2 square root b, everything divided by square root a x minus square root b. And the variable of integration right now is x. Okay, so all I did there was partial fraction decomposition. A little bit ugly maybe if you are looking at that, because I called it a. I could have maybe decided I want to call this thing a squared and that thing b squared, and I think one way or another I have to get through this thing. This'll do. And so I've broken it up into two fractions and did the partial fraction decomposition, found the numerators, and now I'm ready to integrate this thing, and I'm integrating. Okay, let's see. Get all of this out of the way. Now, the reason we do the partial fractions is that we can get these linear, anyway, we can get fractions that we can integrate easier than we could there. Now we can actually integrate each of these, and the benefit with these is they're both linear in x, in the denominator, they're linear, and so they'll go to ln's, and so term by term integration, this is all just a constant, negative 1 over 2 square root b, and then an ln. And then I'm going to put an absolute value because for the moment I'm going to allow this thing to be negative. I'll have the square root of a times x plus the square root of b. Now, what happens if you take an ln of this thing? You'll get 1 over everything inside, and then by the chain rule you'll get an extra factor of square root a. So I'm going to put an extra 1 over root a to compensate chain rule. It's like I did a substitution in my head, or I did substitution, and then after finishing the substitution this would be there because you'd have to substitute u equals this whole thing, and in the derivative you would get that square root of a. Alright, and so the same thing happens when we hit this. We'll get 1 over 2 square root b, and then we'll get an ln of an absolute value, and we'll have all this stuff, the square root of a, x minus the square root b, but then I need to put an extra times 1 over square root a because of compensating the chain rule. Alright, so now let's combine. This constant at the end here and this in the front, and I'll just say negative 1 over 2 square root AB ln absolute square root of A times x plus, I might actually be able to go back and say that this is positive because of restrictions on the velocity being between 0 and that terminal velocity. Perhaps I could do that. I don't have to, though. I think that's just extra time I don't have to do. I'm just going to leave this absolute value to ensure that this argument is positive. And then, just like in this first term, that square root A at the end, I'm going to combine it with this square root B. So I'll make this 1 over 2 square root AB, and then ln absolute square root of A x minus the square root of B. And there would be a plus c from the constant of integration. I'll get to that as I complete the complete the differential equation. I'm just doing the integration. Arbitrary constant comes at the end. Plus I have room. I'll put it there. So then it would really technically have to be there. Okay, now these are both ln's, and so I can combine those ln's, and this one is the one with the negative, so what I'll look for is to put this guy on the bottom. And of course there's a 1 over square root AB. I can factor that out. So I think it doesn't really matter which one goes on the bottom. You know what? I think what might be kind of nice is if I factor out a negative. Doesn't matter. Get to the same result in the end, but let's take out the negative. So then you will have, if you factor out a negative, you'll have ln absolute square root of A x plus the square root of B, and then it'll be a minus because I'm factoring out a negative, ln absolute square root A x minus square root B, all plus the constant of integration. Now I wish I could scroll. I need to keep all this stuff. We'll just have to keep that in memory and start a new page, and I need to begin with this line because one last step is to put the two ln's together. So let's do that. I have negative 1 over 2 square root AB ln just thinking back to make sure that I wrote down, hopefully I had that in memory correct. Alright, that looks pretty good, and that was the left hand side of my differential equation. So that left hand side, I can combine these two ln's. So on the top I'll have square root A x plus square root B, everything divided by, and because of that minus right there, this whole thing goes into the denominator, square root A x minus square root B, and that's plus some constant. One last little thing that I want to do to rewrite this for something I'll connect to later is I'm going to multiply. If I have the square root of A x plus square root of B, on the bottom I have square root of A x minus square root B. I'm going to multiply 1 over square root B, and on the bottom 1 over square root B. So if I multiply in the numerator by 1 over root B and in the denominator 1 over root B, B is not 0 and it's not negative. I'll get negative 1 over 2 square root AB ln, this will be the square root of A. Let's write it like this. Take a little step of simplifying as I'm doing it and just say square root of A over Bx minus 1, and on the bottom a square root of A over Bx. Oh, sorry, the one on top is the plus and the one on the bottom has a minus. Minus 1 plus some constant from the integration. Okay, The reason to do that was that it was one side of a differential equation that I had to integrate. So let's take that and put it back where we were. So we're going to hold on to that and move on to the next page using that result. So actually, to just reiterate, the result that I just got was this integration using Calc 2 partial fractions. It turned into negative 1 over 2 square root AB ln square root a over bx, and then we have a plus there on top, and we had square root ab x, and we had a minus 1 on the bottom, and that was the Calc 2 partial fractions. Now why did I do that? Because I was solving this equation, and I had written it as separation of variables. Let's say we had k over m v squared minus b, and we integrated with respect to v, and that's equal to an integral of 1 with respect to t. And this is what I was calling the left-hand side, and this is what I mean by the right-hand side right now in this differential equation. And so that left-hand side, I did all the work up there on the and have the result where I could say A is k over m, and the B is just g. And so this whole left-hand side becomes negative 1 over 2 square root of my A, that's k over m, times the B, and that's just g, and that's times the ln of, okay, we've got square root A k over m, and that's over g, and I have a variable of integration right now that's v, so I'm switching out of x, I'm switching it to a v, plus 1. And I have a square root A again, well, it's the same thing, it's going to be k over m. I kind of wish I had simplified that before I plugged it in, but anyway, here it is, v, and then it's minus 1. And then on the right hand side it's just going to be t plus some other constant. So that's a first constant, there's a second constant. You know I'm going to combine those constants. Hopefully if you did any differential equations, those constants go together, become one arbitrary constant. So that's good. I'm getting close, but actually I forgot what I really want to do is change this ln into a hyperbolic trig, and that's how I'm going to get v by itself, because how do you solve for v when it looks like this? I don't want to. I want to change, so I've got another little piece of the puzzle that I want to work on, so we'll go to that next. Okay, so rather than trying to solve for v when I had that crazy looking ln expression, I'm gonna rewrite, and that's another kind of like pre-calc topic that I thought would be kind of good to add in here as kind of review in the differential equations. So I want to prove that 1/2 ln, let's say x plus 1 for now, over x minus 1, that something that has that form, I can simplify it and write it as a hyperbolic tangent inverse of x. But I can specifically do that in the case that the absolute value of x is less than 1. Let's just do that in general and pure mathematics, and then we could talk about whether that condition is met in the context that we're working with and what the x really is and so on. You can see that I just had this thing that I needed to try to solve for v in this kind of, so it'll be easier if I write it like this. So let's do that. So what we'll do is we'll say y is 1/2 ln x plus 1 over x minus 1. If I start with that, and then I multiply both sides by 2, and then I use the definition of the ln, or let's not the definition precisely, I should say it's the inverse properties of the ln, the fact that it's the inverse of the exponential. I can say that e to the power 2y would just be this absolute value of this fraction using inverse property of ln. Or you could say make both of these exponent for the exponential, and that's okay because the exponential function is 1 to 1. Alright, from there I want to get rid of the absolute value to be able to solve for x. And I'm going to be able to get rid of the absolute value because I know that the value of x in absolute value is less than 1. So that means it's between minus 1 and 1. So if I rewrite this, e to the 2y is now x plus 1 is positive because at the most negative we've got a minus 1 here, and it doesn't actually go that far. It goes down to minus 1, but it isn't that. So you can go down to 0 in the numerator. Now in the denominator, since we can have down to minus 1 and up to positive 1, what I could do is say 1 minus x to keep this positive. Let's see how to say that. If you've got x in absolute value is less than 1, that means that x is between negative 1 and 1. Suppose if you have the absolute value of x less than 1, then you know that x is between negative 1 and 1, and if I multiplied both sides of both inequalities by a negative, then I have 1 greater than minus x greater than negative 1, and then I can add 1 to all three parts or both sides of both inequalities, so that becomes 2 greater than 1 minus x, which is greater than 0. So I can see that this 1 minus x quantity is between 0 and 2, and so that's how I can drop the absolute value. It's because that's what that's doing there, is it's ensuring that we can drop the absolute value, but that we have to write it this way as a 1 minus x, because x is, let's say, at the most a 1, and that means you have, well, actually it never reaches 1, so you have always positive, close, but closer to 0 as you approach 1. And then you go down to negatives. Of course, this thing is positive when you plug in negative x's. Okay, so that clears up. I got rid of the absolute value, and I want to solve for x. So solving for x, okay, and from here now let's actually solve for x. We cross multiply 1 minus x times e to the 2y would have to equal x plus 1. And so distributing, I have e to the power 2y minus x e to the power 2y is x plus 1. Let's see, how about we want to put all the x's on the same side, so why don't we go x plus x e to the 2y, and then minus 1 we'll have e to the 2y minus 1, and factoring out the x. Factoring out the x, it looks like this. Solving for the x, I'm going to divide both sides by this thing. I'll have e to the power 2y minus 1, that's the numerator, divided by this thing. It's going to be it's going to be 1 plus e to the 2y. Now I'll change a little bit the way it's written. It'll be e to the 2y minus 1 over e to the 2y plus 1. And to get to the form that I want, I'm going to multiply the top and bottom by 1 over e to the y. So I can say x is, this will be e to the y minus e to the minus y, because you have e to the y in the denominator. And then when you multiply this on the bottom, you'll have e to the y plus e to the minus y, and that is the hyperbolic tangent of y. Okay, so let's back up, take stock of what we have so far. I had started off actually here, and I said y is 1/2 ln. It said y is 1/2 ln x plus y over x minus y, and then I took that equation and came up with that x had to be the tangent hyperbolic of y. And so then I could say, by isolating y, I'll take a inverse tan hyperbolic both sides. So tan hyperbolic inverse of x is y. So that establishes this equality. Let me go back and sort of address one thing, that this is actually a condition that's actually met within the context that we were dealing with. If you look at, I had something that looks like -1 over 2 square root AB ln square root a over bx plus 1, and on the bottom I have the square root of a over bx, and it's -1. So I'm gonna, for the moment, rename this thing. This is the x. So I really need to say that the square root of a over b x is less than 1, like that. But remember my a and b. A from before, what was it? K over m. And the b, that was just g. So what we really need is the square root of k over m all over g. That's an m. Oh dear. I need this less than 1. That is, copying that, absolute value, square root, that's k over mg x less than 1. And that's met as long as this quantity is between -1 and 1. So let's say square root k over mg x, and that's got to be less than +1. And let's take k positive and m positive and g positive, since we've had those assumptions from the very beginning, and multiplying both sides of each inequality by that, I can say negative square root mg over k less than x less than square root mg over k. So as long as I'm within the terminal velocity, that condition's actually met in this particular ln function. So I'm going to be able to write it as a hyperbolic tangent because I have that condition, exactly that condition met in this expression with those values of a and b. Beautiful, right? All right, so let's continue. Right, you see what this is terminal velocity. These are the bounds of the terminal velocity. Alright, the point that I've reached so far is that I can write -1 over 2 square root AB ln. I can write that in terms of a hyperbolic tangent inverse. The ln of this fraction is a inverse hyperbolic tangent. And so I'm going to get, let's say, -1 over square root AB, because the 1/2, you can see, sort of disappears. Let's say it's that I've got a factor of -1 over square root AB that isn't here in this formula. So let's say how about if I said it like this? It's then times 1 over 2 ln, that's a 2. So what I'll do here is I'll just say that what was x before is now, this is the x. This whole thing is the x. So it's -1 over square root AB. Or you might just substitute. You could say like u equals the square root of a over b x. If you did it that way, it'd work out the same thing I'm going to do. I'll just say that's the tan hyperbolic square root a over b x. Okay, so let's go back to finish off this differential equation. This left-hand side, I can write it as an ln, but I can also write it as -1 over the square root of AB hyperbolic tangent inverse of square root a over b. But the variable right now is v. The variable of integration is v. And okay, I had a constant on both sides. I'll combine those two constants into one single arbitrary constant, because there's a constant of integration on both sides, but they can combine into one single constant of integration. So we'll say, how about -1 over square root AB tan hyperbolic inverse of the square root of a over bv, like that, combining those two constants. Now I'm solving for v, and all that work with the proving that the ln can be written as a hyperbolic tangent makes it much easier now to get v by itself. Let's first multiply by this 1 over square root ab, so then we have tangent hyperbolic inverse of the square root of a over b. V is, okay, negative square root AB times t plus, and I'm going to rename the c again because I'm multiplying by a constant, so an arbitrary constant times some constant square root AB, just another constant. Now I can get the v by itself by writing, taking a hyperbolic tangent of both sides. So we have the square root of a over b. V is hyperbolic tangent of negative square root ab t plus the constant. So I take a hyperbolic tangent of both sides. Just almost got the v by itself. One more step. So we're here and we're solving for v. So we'll say v is square root of b over a hyperbolic tangent of negative square root a b plus c. Now we can go back and put in what the a and the b were in terms of those original constants m and g and k and so on. So a was, let's remember, what was it? A was k over m. Gotta be really careful. I don't want to have that up to mess up everything. So a is k over m, and I can remember that b was g. So v as a function of t is the square root of, I've got g on top, a is a fraction k over m, hyperbolic tangent of negative square root, and a was k over m times g. And then the independent variable t plus some arbitrary constant from the integration. So let's take one step here. We're dividing by a fraction, so we can say square root. So then we get the m on top, mg over k. That might look familiar. That's the terminal velocity showing up in the formula for the velocity as a kind of constant factor out here in front. So let's just write this as like kg over m. It's not the same. It looks like that. Now, hyperbolic tangent, if you plugged in 0, what I want to do is I want to get the constant. So I'm going to use v of 0 is 0. I'm assuming that the object's dropped, and so under the conditions that the object was dropped, I can figure out what that constant would have to be. We'll see it's going to be 0, and that's because if you take the tangent hyperbolic of 0, tangent hyperbolic of 0 is e to the 0 minus e to the 0 over e to the 0 plus e to the 0. So it's 0 on top, 1 on the bottom, so it's 0. So if you plugged in 0 for time, I have to get 0. So this is mg over k hyperbolic tangent of 0 plus c. And so hyperbolic tan looks like this. It has asymptotes, and it's a 1-to-1 function, so it's going to up like this and then go like this. So the only value that's going to give you 0 is 0. So it's that fact that tells me that c is 0. Right, this is graph of the tangent hyperbolic. So if you just graph that by itself. Alright, so now I got the constant. So now I can write the velocity function. It's the square root of mg over k tangent hyperbolic no, not inverse, sorry. The inverse disappeared. I still have a negative inside there. I found the c was 0. But also, hyperbolic tangent is an odd function, so I can factor out that negative. You can see it's an odd function because plugging in a negative x is the same as plugging in an x and making it negative. So the negative comes out. So that's it. That's the velocity. The graph's going to look like this because I'm taking negative to be down. So it'll start at 0. This is my terminal velocity here. Negative square root mg over k, whatever that is an asymptote because it was a critical point for the autonomous equation. And then hyperbolic tangent, when you take hyperbolic tangent and you multiply by a negative constant, you're going to flip it upside down, stretch it, so it's going to do some kind of graph like this, some kind of curve that goes like that. So the object starts at 0 velocity, gets faster and faster until it reaches this terminal velocity, which is this quantity, terminal velocity, but negative in the orientation that negative is down. So this is time. This is time here. And whatever units you're using, that's seconds. And then this is the velocity. And this is both valid for feet per second or meters per second for the velocity. Alright, so this is a pretty good achievement right there, a formula for the velocity of an object that falls with air resistance. And we can go one step further and derive the position function as well by just integrating the hyperbolic tangent. So in order to do that, that one last step. In order to get that specific result in the context of the velocity of a falling object, let's just look back at how could you approach something like this, just integrating a function of this form, hyperbolic tangent. Let's put a constant in there. So just say, with respect to t, where a and b are positive constants, well, what I'll do is I'll write it as a constant a, and then I'll change this for the way that I want to explain it, because I want to give it, I don't want to just say what it is, I want to sort of derive it in some way based on something you already could find out, something you've already seen perhaps. In fact, I kind of regret it, I didn't say it real clear before, but this hyperbolic tangent is really just a combination of exponentials, and it looks like this. And it comes from the fact that sine hyperbolic was e to the t minus e to the minus t, everything over 2, and cosine hyperbolic is e to the t plus e to the minus t, everything over 2. And if you divided these two guys, you would get this hyperbolic tangent function. So these hyperbolic trig are really just a particular combination of the exponential e to the t and e to the negative t, some linear combination of those two functions, e to the t and e to the negative t. Defined precisely in this way, these exponentials have some properties that are similar to the trig functions in many really intriguing ways, and that's how they get this name, sine hyperbolic, cosine hyperbolic, etc. So just for the purpose here, just to sort of make a connection to some basic calculus, I'll integrate with the exponentials, even though there's other quicker ways I could do this. I'm going to go just for the sort of benefit of deriving from things that I hope that you already know. I'll write it in terms of exponentials. So let's say tangent hyperbolic is e to the t minus e to the minus t, everything divided by e to the t plus e to the minus t, and then I'll do a substitution right there. And the substitution I'll make is this thing on the bottom. So du, oops, I'm sorry, this is a hyperbolic with a b. So if you had a b in the argument, you'll get a b in every one of these. So this is b, negative b. And so that's what I want to substitute. So the derivative would be, because of the derivative of the exponential, I get an extra constant b, e to the bt, and then a minus b, e to the minus bt, and because I'm writing the differential, I'll say times dt. And then I can factor out the b, and now I'm going to go back and substitute. So I have a constant a. In the numerator I have e to the bt minus e to the negative bt. In the denominator I have substituted u, and then to replace the dt, it's du over this whole thing with a b e to the bt minus e to the minus bt, and that's perfect because those guys cancel. So it becomes an integral of a over b 1 over u with a variable of integration of u, and so that's a constant ab ln absolute value of u plus the constant of integration, that's a over b ln, and the u, that was this thing, so that's the ln of e to the bt plus e to the minus bt. Now I want to turn this into, I can rewrite this. It'd be helpful to, there's another alternate way of writing this combination of exponentials, and so let's do that. I just worked out that this is a over b ln absolute e to the bt plus e to the minus bt plus a constant. Alright, the trick that I'll play here is I'll go a over b ln e to the bt plus e to the negative bt, and that arbitrary constant, I'm going to take out a factor. This is pretty fancy stuff, but I'll say let's just take an ln of 1/2 plus a different constant from the one that I had there. I don't really need this stuff down here anymore. Right, so that arbitrary constant I can split up into the ln of 1/2, which is a fixed value, plus some other arbitrary constant, and now I have two ln's both of which have positive arguments, and I could just multiply together the arguments and say it's one single ln. In fact, I'll put an a over b in front here, because then I can really combine them. So I factor out the a over b. So this specific constant a and b and ln 1/2, but then some other arbitrary constant c2, that all together make up this arbitrary constant c1. That trick allows me to say a over b ln of 1/2 times this argument, which means I could just write it as e to the bt plus e to the negative bt, all divided by 2. And maybe you kind of know why I would want to write it that way, and I'll just rename. It's just an arbitrary constant out there. It's because this is the hyperbolic cosine. So this is a over b ln hyperbolic cosine of bt. And I have a plus constant there, and now hyperbolic cosine kind of looks like, oh, that's not sloppy. So hyperbolic cosine is always positive, and it kind of looks like that. So we can actually drop the absolute value. A over b ln hyperbolic cosine of bt plus some arbitrary constant. That's what happens when you integrate a hyperbolic tangent. You get the ln of the hyperbolic cosine. So now I can use that to integrate the velocity. So let's finally do that. We'll get the height. So where I was, velocity is negative square root mg, which was, by the way, terminal velocity, hyperbolic tangent of square root of k times g over m times t, and the constant is 0 because the initial velocity is 0. And now if I integrate, the height function will be the antiderivative of the velocity. So you see now why I was integrating hyperbolic tangent with these constants, integrating with where the variable of integration is t. So this is a constant, and just exactly following the rule that I had before, it's a over b, right? So it's negative square root mg over k over that thing, square root kg over m ln cosine hyperbolic of that argument. Plus a constant from the integration. Another way to say this that I could have done before, I just wanted to show the substitution. I could just say that the derivative of the ln of cosine hyperbolic would be 1 over cosine hyperbolic, and the derivative of cosine hyperbolic is sine hyperbolic, and that would produce sine hyperbolic over cosine hyperbolic, which gives you this tangent hyperbolic. And I need to put this extra 1 over square root kg over m here in the front to cancel the chain rule factor that this thing produces. Now these are both square roots, and I can combine it into one big square root. Let's say it would be mg over k, that's on top, times, when this thing gets flipped because it's on the bottom, this is m on top and kg on the bottom, ln cos hyperbolic square root kg over m. Now let's see, g's cancel in this. That's m squared over k squared, and both are positive, so you can just take the square root of m squared. You just get m over k. Because the square root of m squared, the square root of k squared. That simplifies just m over k, ln cos hyperbolic square root kg over m t plus the c. Now, the last piece would be, what about the constant? Let's say that height at time 0 is this constant initial height. So if you plug in 0, you have to get the height is h of 0. So h of 0 is the result of plugging 0 into this right-hand side. Negative m over k ln cos hyperbolic, t is 0, so that's 0. But the cosine hyperbolic is 1. When you get 1, you have the ln of 1. So that's the ln of 1, and the ln of 1 is 0, so that means h of 0 is the constant. So we just about have it. Let me just write this whole thing out now. That is now a formula for the height over time. It's going to look something like this. It starts off at h0, and then it just drops, and over time the height will go down to 0. It looks like a parabola, but it is not a parabola. It's the natural log of the hyperbolic cosine, which I think it's a little wider maybe than it would have been if you had no air resistance, right? It's because it's not going to fall as fast, so the height drops. Maybe the parabola is somewhere in here, and this thing is not falling as fast because of the air resistance. So a very small difference. I mean, most of the time, of course, in pre-calc classes, we ignore air resistance and we just say it's quadratic, a parabola, without, it's just proportional to the square of the time, and just get a parabola. But it's a little more accurate here. So why don't we finish this off by looking at a particular example with values for m and k and of course the constant acceleration due to gravity, and a particular given height, and see what the curves look like. Okay, so I've derived these formulas for velocity and height with an object that's falling with air resistance, and I would expect a graph from the hyperbolic tangent with a negative in front to look like this, to approach asymptotically this square root negative mg over k. That is the terminal velocity, so it approaches that over time. And the graph of the height, it looks kind of like a parabola, but it's this ln of the hyperbolic cosine that has this initial height, and it just falls, and then when it hits here, this is 0 height, so that t-intercept, just like it's always been, it's the time when it hits the ground. So why don't we start with some examples. I looked up a baseball, and I thought that was about 143 grams. Let's take a height of 50 meters. And that's the initial height. Let's go with k. This let's go with 0.3, and this is sort of like newtons per velocity squared. So those would be the units of my drag coefficient, and we'll take of course with these units we've got acceleration due to gravity is 9.8 meters per second squared. And if we plug those into these two formulas, what do we get? Well, first for the velocity, it's negative square root, the m is 143, g is 9.8, positive, I got the negative in the formula, over the k, that's 0.3, hyperbolic tangent, that's my velocity function, square root, now I've got k, 0.3 times g, 9.8, over m, which is 143 grams. And this is times t. So typing this in, it's about negative 68.3 tangent hyperbolic of about, let's say, 143 t. So this is negative 68 meters per second is the terminal velocity right there. Okay, we could graph that in a second, but let's just write out our height function and then I'll graph them both. So let's figure out, now we've got negative m over k, so this is negative 143 over k, which is 0.3, natural log hyperbolic cosine of, it's the same coefficient here, so, well, I'll write it, it's square root 0.3 and 9.8 over 143 again, t, and I had an initial height of 50 meters. So this whole thing will work out to be about negative 4, this dividing this is negative 476.7 roughly, natural log cosine hyperbolic of that same coefficient 0.143t plus 50. So those are two functions that I want to graph. So let's take a look at what that looks like. So I typed in my velocity function, and the part that really is relevant here is only from t positive and on. So it looks like within about 10 seconds it's reached its terminal velocity. Well, maybe certainly within 20 seconds it's pretty close to the terminal velocity, which is negative 68.3 meters per second, and that's about 153 miles an hour. So it'll fall faster and faster, about 150 miles an hour, and then it just won't fall any faster than that because of the air resistance. So let's take a look at the height. So the height function is like negative 476. Sorry, yeah. But it's an ln of a cosine hyperbolic, 0.143t. But then we had that initial height of 50, so it puts it like that. So let's zoom in a little bit. So it looks like it's going to hit the ground in about 4 point something seconds, less than 5 seconds, that it will hit the ground from a 50-meter height. So that 50-meter height, that's about 160 feet. So yeah, so it's falling and picking up initial velocity is right here. The red curve is the velocity, the blue curve is the height, and I can see that it's falling faster and faster. Let's zoom out a little bit until, let's see, well, I can certainly see that by the time it hits the ground, it's still picking up velocity. So I can say one thing is that it does not reach its terminal velocity as it's falling. It would have to be dropped from a higher altitude in order to reach that terminal velocity. That terminal velocity isn't really going to reach that until maybe after 20 seconds. So it'd have to be much higher up in the air and dropped to ever pick up that kind of velocity. So, all right, I think that's about where I think I'll end with this exploration. Pretty neat little derivation for modeling objects falling with air resistance.